This week, we're talking about factor analysis. And we're going to start by talking about its relationship to principal components analysis and some of the basic exploratory factor models. We're going to focus on exploratory factor analysis, though I will touch on confirmatory factor analysis towards the end. So far we've learned about principal components analysis, which is a purely data-driven approach to understanding how we can transform our data into a set of orthogonal components that capture the shared variability among all of our variables. Exploratory factor analysis, EFA, is similar, but it's a bit different, and it's a bit different conceptually as much as it is computationally. So one way to think about it is that in EFA, or this should say PCA. In PCA, we have P components. And in EFA, so in PCA, we have P components, and these are just transformations of the data itself. So there's always P total components equal to the number of variables in the data. We just transform the data into these P new components. In EFA, we're assuming that we have some number of M, which is less than P, factors, which are unobserved variables that capture the correlations in the data. And EFA is about understanding these correlations in the data. And then in EFA, because there are fewer factors than total components, there's still some specific variability that's specific just to the variables themselves that doesn't actually influence the correlations between the variables. So the simplest factor model is the orthogonal factor model. In terms of, when we think of in terms of the data, we could think about it as we're modeling the mean-centered data, so that's n by p, based on a matrix of unobserved factors. So these are unobserved variables. M, in this case, we have m unobserved variables, so we have an n by m matrix. And then we have factor loadings, which is an m by p matrix. So these are the coefficients that you multiply the factors by to recapture the correlated parts of the original data. And then the leftover information is this epsilon term. So because the factors don't fully recapture the data, they only recapture the correlations in the data, we need to explain the remaining information in each variable that's not captured just by the correlations. And so this is a specific factor, or the uniqueness. The book flips things around a little bit in the way it does the notation, and just for simplicity, I'm going to follow that moving forward. This isn't structured in terms of the data so much as it is in terms of these different sort of components of the data. So here, x minus mu is p by 1, L is p by m, f is m by 1, and epsilon is p by 1. I find this a little bit less intuitive, but the notation moving forward is a little bit more comparable to what you see in the book, so I'm going to stick with it. And it's not that important. So because f and epsilon are unobserved variables, we have to constrain them in particular ways to make the model identifiable. So we're going to set f, which is the factor scores, to have a mean of 0 and a covariance matrix of identity. So they are orthogonal, they don't have any correlations, and each one has a variance of 1. We set the mean of epsilon similarly to be 0, and we give it a covariance of psi. So psi is a diagonal matrix, but it has zeros off the diagonal, just like I, but we're not constraining the variances to be 1. We're actually estimating the variances of epsilon. So constraining our variables in this way has another nice property in that it lets us define everything in terms of the covariance matrix of our original data, sigma. So we can define sigma now as the loading matrix times itself plus psi. And so this is convenient because we don't have to worry about the unobserved factors. We can just estimate the loadings based on the covariance matrix and psi. So this saves us some estimation, and in fact makes it so we can estimate the model. So we are now going to define the LL matrix, so L times L transpose, as a P by P matrix that represents the shared information between the variables on the M factors. And the P diagonal elements of the LL matrix are called communalities, and we're going to denote these H squared. So each variable has an H squared. So this is the information that is this is the information in the variable that's related to the shared information across the variables. So it's what information that goes in, it's the information that goes into each variable that is accountable by the correlations in the data. Another way to think of H squared is it's like an R squared value for each variable regressed on the other P minus 1 variables. So when we're dealing with correlation matrices rather than covariance matrices, that it actually becomes defined as this R squared value. So it's between 0 and 1 because remember, we're finding the diagonal, which the diagonal of a correlation matrix has to be 1. So and this is a component of that diagonal, so it has to be between 0 and 1. And so it is actually the R squared of each variable regressed on each other variable. So the off diagonal of the LL matrix are the covariances or the correlations between the original P variables. So this LL matrix is capturing the correlations in the data and the amount of information for each variable that's attributable to those correlations. Then the specific variability, the uniqueness, is captured by this psi matrix. So this is the diagonal matrix of specific factors. So this is the remainder of the variability in each variable that's not attributable to the correlations. This is unique information in each variable captured that's not captured by the M factors. So a small example that the book gives is on pages 484 to 485. I'll show you how to do it in R. So here I'm just going to define a covariance matrix, and I want to decompose this into the communality matrix and the uniqueness matrix, the specific matrix. So here I'm going to define the factor loadings at L as these values. So this is the driving the shared variability in the data. And then psi, which is the unshared variability in the data, as this diagonal matrix. So what I'm going to do is multiply the L matrix times its transpose and add psi. And you see that if I do that, I recapture the original covariance matrix, the original data. So the way we would interpret this is that the first variable in X, which if we mean center it, so the mean centered X can be expressed as a linear combination of the two factors plus some residual error, which is actually just the specific variability so x1 minus mu1, so the original X minus its mean is equal to 4 times the first factor plus 1 times the second factor plus the element of plus the specific variance. And this has a mean of 0. So epsilon is going to have a mean of 0 and a variance of 2. So remember, this is recapturing the covariance matrix, not the data itself, but it does give us the factor loadings. So these are the factor loadings. So this is where I got the 4 and the 1. It's the first row of the loading matrix. So it's 4 times the first factor and then 1 times the second factor. Would recapture the actual data. What we're doing here is recapturing the covariance matrix. These are also the coefficients if we had real data to get the factor scores. And so we can do the same thing for the second variable. So there are different ways of obtaining an orthogonal factor model, and how you do it will depend on what you need. So the most data-driven approach, most similar to principal components analysis, is called the principal component solution. So here what we do essentially is we're taking the principal components, we're just keeping the M that we need, and now we're going in reverse. So we're finding the linear combination of those variables that's going to recapture our data. So we're essentially flipping around the principal component solution. We're taking the solved equations and we're rearranging to find the linear combination of components that recaptures our data. Whereas in principal components, we're finding the linear combination of our variables that creates the orthogonal components. So to do this, you go back all the way back to when we learned about spectral decomposition. So remember that we can recapture our sigma, our covariance matrix, based on the eigenvalues and eigenvectors. So the eigenvalue times the it's the sum of each eigenvalue times its eigenvector times its eigenvector transpose. This will recapture our original covariance matrix. So conveniently, this links to our definition of the orthogonal factor model. So we can write L transpose as the same thing, except instead of going from 1 to P, we're going from 1 to M. So we're just using the first M eigenvalue eigenvector pairs to get our loading matrix. And because L is already L times itself, all we have to do is essentially take the square root of this formula to get just the loading matrix on its own. So we're just taking the square root of the eigenvalue times the eigenvector. That gives us our factor loadings or our communality. So for the M factors, and then to get the specific variance, we just subtract the diagonal of L times L transpose from the observed covariance matrix S, and that gives us psi, which is the leftover information for the remaining P minus M components. Another issue that we often consider in factor models is called rotation. So orthogonal rotation is based on the idea that it's possible to essentially manipulate the axes of the orthogonal factor model and transform them so that they really best align with the original data. It's a way of making the factor solution a little bit more interpretable. So essentially, mathematically, what we're saying is that we can multiply L by any conformable orthogonal matrix and still recapture the original covariance matrix sigma. This is because if T is orthogonal and we define L star as L times T, then L times L transpose plus psi is equal to L times T transpose, which makes, because T times T transpose is just identity, it's 1 because T is orthogonal. So that means that this is still equivalent to L star times L star transpose plus psi. So we still capture the same total amount of the variability in our communality by rotating the L matrix as we would if we didn't rotate it. So what we're trying to do is try to find a rotation that will make our L star the most interpretable possible set of factor loadings in terms of our original data. So it's also worth noting that when we set M equals to P, we're actually just using the each principal component to estimate the factor solution. And the orthogonal factor model becomes equivalent to the principal component solution. The main difference is just the direction we're going in. So in principal components analysis, we're finding coefficients for our variables to define the components. In factor analysis, we're finding coefficients for the factors to recapture our original variable. So it's just flipping the math around. When M equals P, when M is less than P, we're adding some constraints. So this is the example we're going to look at today is based on the data from the WAIS-R, which is an older version of the Wechsler adult intelligence test, which is an IQ test. This is from this following paper. It's actually available in an R package here, which is where I got it. I just cleaned up a little bit to make it a little bit easier for us to use. So we're going to look at this from a more theoretical lens later, but to start out, let's assume that we don't really know much about the structure of an intelligence test, and we're trying to investigate what that structure might be based on the data. So what the first thing that we might want to look at to start to triangulate how many factors we want to focus on. So we can look at a Scree plot. So we can do this just like we saw last week. Since we're using the principal component solution, we're going to use the principal component Scree plot. Just like we saw last week. So this is the same code for running the Scree plot that we saw before, and here I'm doing it with a parallel analysis. So these results suggest we definitely want the first component, and then maybe the second component. It's a little bit hard to tell. It's below the parallel analysis line, so strictly based on the parallel analysis, we probably wouldn't necessarily keep it, but it's close, so we might want to consider it. So let's go and look at the factor loadings and then determine if we want to interpret the two-factor solution or not, or just the one-factor solution. So we can get the unrotated factor loadings just based on the eigenvalues and eigenvectors. So we just multiply the square root of the first eigenvalue by the first eigenvector. So these are unrotated factor loadings. And these will be the same no matter how many factors you use in the unrotated solution. So this is pretty straightforward. It looks like each of the variables has a pretty high and similar association with the original data. Or with the first principal component. So the first principal component loads pretty highly, or the first factor loads pretty highly on each of the variables. So here we can get the second set of factor loadings. So this is if we wanted to do the two-factor solution. And so it's not super clear that there's much going on here. None of these sort of jump out and yell that they're loading highly onto the second factor. So we can use the principal function from the psych package to get these same results. When we don't ask for any rotation, the first m factors are always going to be the same no matter how many you ask for, because they're just based on the principal components. So we can get the loadings with the loadings function, but it's going to, by default, suppress anything with a value less than 0.1 and just ignore it. So here is the first set of loadings. This matches what we got before. The signs are flipped around, but that's not important. And here's the second, again, matches what we got before. So should we stop here, or is there a way we might be able to better interpret our results, especially for the two-factor solution? So these are unrotated factor loadings, and so we can still try to find a rotation that might give us a better interpretation for the second factor. This isn't really easy or practical to show by hand, at least as far as I know, but it's easy to implement in the psych package. So one of the most common orthogonal rotation methods is called Varimax. So let's see what happens when we use Varimax rotation on the two-factor solution. So now we get a much clearer second factor interpretation. So now, or interpretation of the two factors. So we see that the first factor is really being driven by these first four variables, and the second by these last four variables. Notice also now that the first factor on its own is responsible for a smaller proportion of the total variability, and the second one a larger total of the proportion of the total variability, but the cumulative variability between them is still the same as it was in the unrotated version. So this 0.773 is the same, but the distribution across the two factors is different. That's what the rotation is doing. It's taking the total variability and distributing it a little bit differently across the two factors to make it so that the two factors are as interpretable as possible. So we can also look at a three-factor solution here, and now we're sort of getting a little bit messy. It looks like maybe this arrangement variable is loaded by the third factor, but otherwise the pattern's pretty similar. Based on the Scree plot, I probably wouldn't interpret the three-factor solution here. And the four-factor solution is we really aren't seeing much now. Maybe completion is the fourth factor. And notice that some of these are missing. This just means they're less than 0.01 or 0.1. So one thing this highlights is that, and this is an aspect of factor analysis that's sometimes criticized, is that it's pretty subjective. Principal components analysis is purely data-driven. You're always extracting the same number of components, and then you make some subjective decisions about what each of them mean, but you're not making any decisions about how many to estimate. In factor analysis, you are making subjective decisions about how many factors you want to estimate. And this is sort of the art of factor analysis, and it's something that some people criticize, some people think is great, but is definitely an important thing to be aware of. So next, we're going to look at some approaches to factor analysis that are a bit more flexible and rely a bit more on theory and less about the data itself.